So just to start, let us consider, for example, this elliptic equation. So this coefficient Aij, the matrix is elliptic, and I will suppose generally that these are discontinuous. The question, the regularity problem related to this operator, even you can consider also some boundary conditions on the boundary of some boundary domain omega. So the regularity problem of course, I must specify in which functional space is posed this problem, so I will consider mainly the Lebesgue spaces LP. The regularity problem in LP spaces for this boundary value problem asks which conditions. So ask this given a right-hand side F belonging to some LP space, which conditions to impose mainly on the dependence of the coefficients on the variable x to ensure that a solution of this problem belongs to the Sobolev space with the same rate of integrability. So this is generally, roughly speaking, this is the regularity problem for this elliptic operator. I guess you know very well the response of this question when the coefficients are continuous. So if Aij are continuous functions in omega, then you have an affirmative answer of this problem. And this is given by the so-called Calderon-Zygmund theory. I will mention later about this theory. So now I will consider...
For smooth boundary, surely.
For smooth?
For smooth boundary.
Yeah, exactly. For smooth boundary, I will consider bounded domains with sufficiently smooth boundaries. So now the question is that when these coefficients are continuous functions, then you have this regularity of the solution of the problem, and the equation is satisfied almost everywhere for almost all x in omega. And the main question I will consider will be the case when these coefficients are discontinuous. Discontinuous functions. For sure you cannot take any discontinuous functions, so some sort of regularity must be imposed on these coefficients. So I will speak of particular spaces where to take the coefficients. I will mention later, I will define later these spaces, but anyway, this short course here is based on some results proved in the beginning of 90s, so 90 more or less these years here, by 3 Italian mathematicians, Filippo Chiarenza, Michele Frasca, and Placido Longo, who extended the Calderon-Zygmund theory to elliptic operators with discontinuous coefficients. So, let me start now with, I think, with the recall of some functional spaces. Maybe you know very well these spaces. I will use my drafts here, and after I think we may take a copy of this anyway. So let me start with recalling and defining some functional spaces we will use. Of course, in all the course I will consider a bounded domain omega. I mean domain which is open at connected set. N-dimensional domain with smooth boundary. So by the end of the course I will consider also boundary estimates and eventually solvability of the Dirichlet problem for this kind of operators. So I will need that the boundary is C11. It means that locally at each point of the boundary there exists a local diffeomorphism which flattens the boundary. And this diffeomorphism belongs to C11. C11 means that the first order derivatives are Lipschitz continuous. So, well, LP is the space of Lebesgue integrable functions which is known to anybody. So I will consider also the Sobolev space WKP in omega, which consists of all functions, all measurable functions defined in omega with values in R, such that these functions together with all their derivatives up to order k, k is integer, belong to LP. So alpha is a multi-index which is less than k. Maybe in some place I will speak also about so-called fractional Sobolev spaces, but it depends. It depends on the time we have. So these are more or less known spaces. Now I will speak about some particular spaces which are in some sense related to Lebesgue spaces, but are more precise because they take account of the, how to say, of the distribution of the LP normal of the function. The first one is the so-called Mori space. So you are taking some exponent p greater than or equal to 1 and another exponent lambda which stays between 0 and the space dimension n. After that you are doing this way. So I will suppose for simplicity that the function f is defined in all the space. It is not restrictive to consider it to some defined to some domain because it is sufficient to multiply by the characteristic function of domain. So now you are doing this way. You are considering a ball with radius r and center it in some point x0. So this will be a common notation to be used in the sequel. So these are simply the ball centered in point x0 with radius r, the open ball. You are taking the p power of the function f. Then you are integrating with respect to y this power over the ball b rho with center at x0. You are dividing everything this by the lambda power of the radius, raising everything to 1 over p, and then you are taking the supremum with respect to all x0 and also with respect to all radiuses r. In case this quantity is bounded, then you say that f belongs to the Morris space LP lambda. So f stays in this space if and only if this quantity is bounded. And it turns out that this quantity defines a norm in the Morris space LP lambda. Well, what happens in the extreme cases, if you take, for example, lambda equals 0, then this denominator here disappears and you obtain exactly LP. In case lambda equals the space dimension n, then this rho raised to power n is comparable to the measure of the ball with radius r. So here you have the mean integral of f, and it means that this extreme case gives you L infinity because of the Lebesgue differentiation theorem. So what is interesting, what are the interesting cases are the cases where lambda stays between 0 and 10, the space dimension. The Morris spaces, they have various important properties. They are local spaces, and some important facts for these spaces are this one. If you have that f stays in some Morris space LP lambda with exponents p and lambda, it doesn't mean the existence of some better integrability exponent. So it doesn't follow the existence of some q greater than p with the property that f belongs to LQ. So this second exponent here, lambda, doesn't give you some gain of integrability. And the other important property for the Morris spaces is the so-called Morris lemma, which asserts that if you have some function f which belongs to the Sobolev space W11 with gradient of this function belonging to the Morris space LP lambda with p plus lambda greater than the space dimension n. So think for a moment for the classical case of Sobolev embedding. Forget, for example, this lambda. So if you have a function, so here you have to put p. If you have function from the Sobolev space W1p with p greater than the space dimension n, then the function f is Hölder continuous. Okay? With Hölder exponent which equals exactly 1 minus n over p. In this case, if you have the gradient which stays in some Morris space with some of the exponents greater than n, then you can assert that f is Hölder continuous with exponent lambda equals 1 minus n minus lambda over p. So in case lambda equals 0, you have exactly the known embedding of the Sobolev space into the Hilbert spaces. This is more precise result because it gives you the possibility to consider even p less than n, but everything this is on account of the second exponent lambda. Of course, if you consider here, if you consider integration over the intersection of the ball with some omega, given omega, you can obtain the definition of the Morris space over some domain omega, The other class of spaces I will consider, it is number 3, are the so-called Companato spaces. LP lambda, but italic P. Now, italic L. Now P is, as before, greater than equal 1. And the second exponent lambda is greater than or equal to 0 and less than or equal of n plus p. N is always everything, n is the space dimension. Now, I have to introduce some notation. So, for a measurable set E, I will denote f sub E the mean integral of f over the set E. The mean integral, you know, it is the integral of f taken over E divided by the measure of the set E. Well, now I will repeat more or less this definition, but the integrate now will be somewhat different. So I will consider f of I minus the mean value of the function f taken over the ball of radius r. So more or less the oscillation of the function on the ball. Then I will integrate this quantity on the ball. So I will take, after that I will take, well, without taking without dividing of the volume of the ball. So this is a sort of mean oscillation of the function. Here I will put the power p, and I will divide as before everything of the radius raised to the power of lambda. Then you take 1 over p of this quantity, and after that you take supreme with respect to all centers and with respect to all radiuses. In case this quantity is bounded, I will say that the function f belongs to the Companato space with exponents p and lambda. And this quantity, of course, defines a norm of the L of the function f in this space. Excuse me? Semi-norm. Yeah, it is a semi-norm because of the fact that for the constant functions, this quantity could be 0. So it is a norm in these spaces modulo the constant functions. Well, some facts about the Companato spaces. I'm sure that you can find all these facts, all these properties in some by now classical books on functional spaces and so on. Also, some textbooks on partial differential equations, they introduce these spaces. Some facts, some relations between these spaces.
Excuse me. But if I try to define this space over the bounded domain,
yeah.
Then, is it make any difference if you have the average over the ball or over the intersection?
No, you have to substitute the ball just by the intersection of the wall with omega.
Yeah, and average is over.
Is taken over this set, yeah. Is taken over the set where you are integrating. So of course you have to impose some conditions on the boundary, some smoothness conditions on the boundary, and in order to do everything this, it is sufficient to have boundary which satisfies the exterior cone condition. Well, so of course these spaces are known as Companato spaces because it was the Italian mathematician Sergio Companato who introduced them some maybe 50 years ago. Well, now some facts. The first one is shows how the Companato and the Morris spaces are related. So the first one says this. Says this one. The Companato space LP lambda coincides with the Morris space LP lambda. So you have really one and the same space. In case lambda, the second exponent, is in this interval, is strictly less than n. So there is no difference between one and the other. They describe the same space. The third one, well, let me write now the second one. I will turn back later. Ask what happens when lambda equals exactly the space dimension. So you have the Companato space LPn in the case when the second exponent lambda, this one here, equals exactly the space dimension. Now take account of the fact that here you will have the radius rise to the power n, which is more or less comparable, which is comparable exactly to the volume of this ball. So more or less what you have here is the mean integral, the so-called mean oscillation. Companato proved that this space coincides with each other with exponents q and n, and this for each p and q greater than or equal to 1. So independently of the value of the first exponent, the spaces are the same. So you have exactly the space L1n. Here you can put the exponent 1, the first power. And this strange space I will define somewhat later as BMO. The space of functions with bounded mean oscillation. Because you remember, when lambda equals n, here you have the mean integral, the mean oscillation. The power p is 1, so bounded this quantity means that the mean oscillation is bounded, and it is exactly for the bounded mean oscillation space. The more interesting is the third property, which considers the case when lambda, you remember that at the definition, where is the definition? Upstairs, lambda is less than or equal to n plus pi. So the third case is what happens when lambda is greater than n, but it is less than or equal to n plus pi. And what happens now is that the Companato space LP lambda is nothing else than the Hilbert space with exponent lambda alpha, with alpha given by this quantity. It is a lambda minus n over p. So this third property gives you another integral characterization of the Hilbert spaces. So you know that Hilbert spaces, they are defined in pointwise way. So you are considering the ratio of the difference of the functions divided by the difference to some distance in some powers of the points where you are taking the difference in the denominator. So this is a pointwise definition. This way you can have the same, another characterization of the Hilbert classes given in an integral way.
Does Lipschitz continuous function included?
Also the Lipschitz continuous functions are included. It happens when lambda equals exactly n plus pi, because you have here one. Well, okay, so I will clean down the blackboard.
Actually, more lemma is a consequence of this fact. Yes?
Excuse me?
More lemma on that blackboard is a consequence of that.
It could be considered also as consequence, but historically the lemma of Mori was proved before, then Companato introduced these spaces. So after, Companato rediscovered this result, and it is trivial consequence of his result. Yeah. So let me define now the John Mirenberg space. VMO of the functions with bounded mean oscillation. So now I will consider any ball B and the function f as before defined in all the space. So the definition says that the function f belongs to the space VMO, the space of the functions with bounded mean oscillations, if a quantity is bounded. What is the quantity? You are proceeding more or less like here. You are considering the oscillation of the function f over a ball B. You are taking the mean oscillation, so dividing by the volume of the ball B, and then you are taking the supremum of this quantity with respect to all balls B. So small or large balls is independent. In case this quantity, which is called of course mean oscillation, in case this quantity is bounded, it defines a semi-norm. So in case this quantity is bounded, then the function stays in this space. The supremum of the mean oscillations is denoted this way, and it defines a semi-norm. Because of course, if you take a constant function, this will be 0. So this quantity is 0 if and only if f is a constant function. It means that BMO modulus the constant functions is a Banach space with respect to this norm. So this is a space introduced by Fritz John and Louis Mirenberg, and they studied various properties of this space. And as I know, apart from various applications in analysis and mainly in the theory of partial differential equations, these spaces are used also in the approximation theory. Well, some properties of these spaces. Okay, the first one is that BMO, modulus constant functions, is a Banach space with respect to the star norm. Well, it is immediate that L infinity is a subspace of BMO. So if you have an essentially bounded function, then of course the mean oscillation is bounded. So BMO is somewhat larger than L infinity. But what is interesting is that L infinity is a proper subspace of BMO. And you can see this, for example, considering this function, the logarithm of modulus of x. It is by, you can see by straightforward calculation that this function is in BMO, but it is of course unbounded. So BMO is somewhat larger than infinity. Another relation of BMO with some non-functional spaces. Suppose you take f in the Sobolev space W11, so the gradient of f is integrable, but assume moreover that the gradient of f belongs to the Morris space L1 n-1. So the first exponent is 1, but the second one is the space dimension -1. Then you can get that f stays in BMO. I think we may try to prove this. It is not difficult. No, I will use maybe this one. Also this here. So let me remember you the Poincare inequality. So given a function f if w1p, say some omega, with p greater than or equal to 1, and convex subset S of omega, then the LP norm of f minus the mean value of f over S, or the convex subset, is less than, well, the value of the unit ball in Rn. This omega n is an absolute constant depending only on n, is exactly the value of the unit ball in Rn, divided the measure of S, this rise to the power n minus n over n, then you have to multiply by the diameter of S, rise to what power was? P, maybe, or n? No, n. And here you have exactly the LP norm of f. This is a consequence, immediate consequence of the classical Poincare inequality. Well, in order to get this, let us use exactly this form of the Poincare inequality with p equals 1. So I will have here
Gradient.
Is gradient, of course. Of course, is gradient. df in LP over S. So,
the norm is computed over S also?
It is LP norm computed over S. So I will take the ball instead of S. I will take P equals 1. B is any ball. So by this inequality, I will have f of y minus the mean of the ball B, everything integrated on the ball B. This is the left-hand side of this inequality, okay? It will be less than. So now I will put here some constant depending on the space dimension n. Here you have the measure of the ball. The measure of the ball, which is comparable to the radius raised to power n. Here we have this power, so at the denominator you will have the radius, rho of course is the radius of the ball B, so rho raised to n minus 1. Then there is the diameter of the ball, which is comparable to the radius, so rho raised to n, and here you have integral over B of the gradient. Now, what happens now? So what happens now? This guy here, I will move it on the left because I will have to take the mean value here, okay? Because it is comparable to the measure of the ball. So this moves here, and here I will have the mean integral, okay? Now this quantity here is bounded because I suppose that the gradient is in the Morris space with exponents 1 and n minus 1. So this guy here is bounded. And it means, of course, that taking supremum all the balls, I will have bounded mean oscillation. So it proves this inclusion here. And for example, this inclusion is often used when one studies the regularity of solutions to elliptic and also parabolic systems. Okay. How long is 1 hour? 45 or 50 minutes?
As you wish.
50? Okay. Well, another obvious property is that which was written here. Because
the Companato space from third group does not depend on P.
Excuse me?
Does not depend on P, the third group.
In this case?
No, in third.
Yes. Spaces which coincide with Hölder space do not depend on P. So for any P you get the Hölder space, yes?
No, it doesn't depend, but it depends on the values of lambda.
Yes.
It depends on the values of lambda.
Lambda in the...
Lambda must be in this interval here. So you can have even small p, but you have to have lambda large enough in order to get this inclusion here. Okay, the fourth property is which is written here, that BMO is exactly the Companato space with exponents 1 and 10. This one here is the fourth property. Well, And the last one, excuse me?
In the right corner.
Which?
No, you seek for the place.
Here?
Yeah.
Okay. Well, the last property, at least the last in order to understand better these spaces, we have already seen that L infinity is included in BMO. The last property says that BMO is included in LP for each P greater than or equal to 1. So in some sense, BMO is some space intermediate between L infinity and each LP with finite P.
But this is for bounded domain, yes?
Also for Rn.
But how do you get the decay?
Well,
if you have the whole space, then functions from LP, they decay at infinity. And is it true for BMO?
Yeah.
Do they decay at infinity?
Yeah, this property is consequence of this result which is known, and I will use it later, which is known as John Mirenberg lemma. And it says this one: let f be a BMO function in Rn. Then for each p greater than or equal to 1, you have that the mean integral over B, so the mean oscillation, I mean, of power P is less than some constant depending on the space dimension on P times the BMO semi-norm of F. So at least for bounded domains, you have this inclusion, because you can bound LP norm of a function with this quantity. So BMO is in some sense between these spaces, L infinity, some intermediate space between L infinity and LP for each P greater than or equal to 1. Well, our next step is to introduce the space BMO. And BMO stays for vanishing mean oscillation. It was a space introduced by Donald Sarason, and the definition is this one. So take a function f in BMO with bounded mean oscillation. Now do this way. So consider the mean oscillation over ball with radius x of radius r, the mean oscillation. And because of this, you know that this mean oscillation is bounded. Now take the supremum over all balls with radius r, so over balls with radius r, and then you are taking supremum with respect to all radiuses less than or equal to some fixed value r. This is bounded. And I will denote this quantity this way, gamma sub f of r. this is bounded, of course. Now I will say that f stays in VMO. So this is more or less mean oscillation on balls with radius r. Now I will say that f stays in the space VMO, vanishing mean oscillation, if this mean oscillation vanishes as the balls shrink in a point. So if the limit of this quantity when r tends to 0 is 0. So you see that you have a sort of continuity here. But it is not a continuity in the point-wise sense. It is a continuity of integral sense here, in this way, in the sense of mean oscillation. And we will see now, by means of different examples, that you have really functions which could be discontinuous, but anyway belonging to this space. So, in order to fix the concepts, I will call later gamma f, I will call it VMO modulus of f. And the first obvious property is that the space of bounded uniformly continuous functions and uniformly continuous functions is contained in VMO. In fact, in this case, it is sufficient. So here you have writing the mean value of the ball over the ball. Here you can reduce this integral to another integral where in the integrate you have the difference of the functions taking it to different points. So if f is a continuous function, you can estimate this term, the mean integral disappears, so you will have exactly that this quantity tends to 0 thanks to the absolute continuity of the integral. In fact, in this case, you can take as VMO modulus, you can take the continuity modulus of the function f. What is interesting is that this inclusion is proper, and in order to see this, it's sufficient to consider, for example, this function, square root of logarithm of modulus of x. It is, of course, discontinuous function, but by direct calculations you can see that it stays in VMO.
You mean at infinity?
Excuse me?
Sorry, you mean at infinity?
No, what happens at infinity, it is not interesting. It is interesting what happens at the 0, at the origin.
Then logarithm is negative, and what does it mean, square root?
Well, excuse me. All right. Okay. So VMO contains the space of bounded and uniformly continuous functions. So this is more or less trivial. Now we will see that inclusion of W1n into VMO. So the Sobolev space W1n, each function in this Sobolev space belongs also to VMO. In order to see this, I will use once again the Poincare inequality in its original form. So, I will do this way. I will consider the mean oscillation over ball of radius of some radius. Okay. Then I will take the mean value, and by the Poincare inequality, this quantity is bounded by the ln norm of the gradient taken over the ball. So it is less than this quantity here. It is by Poincare inequality. Now, even if the ball, so now assuming that the ball is of radius r, taking the supreme of over with respect to all the balls, and then putting r tends to 0, this quantity tends to 0 because of the absolute continuity of the integral. So it means that the function will stay here in VMO. Moreover, arguing in this way, you can prove also that the fractional Sobolev space with exponents theta n over theta is contained in VMO. So here theta, of course, is between 0 and 1. Well, I don't know, we can do the calculation. I don't know if it is worth to do it. You know the fractional Sobolev spaces, yeah? Well, let me just recall the definition of the fractional Sobolev space. So W say some SP in omega, for example. So this is the collection of all the functions defined in omega with values in R, such that F stays in LP omega, and such that this quantity is bounded. So first of all, I will have to write S like sum of its whole part, some integer here, the whole part, plus the decimal part sigma. And then I will have to consider what? For a multi-index alpha of length, the whole part of S, I will have to consider this quantity raised to the power p, here, the exponent p. Then I will have to divide to x minus y raised to the space dimension n plus this decimal part sigma times p. Okay?
But only for sigma non-zero.
Yeah, for sigma greater than 0, less than 1. Less than 1. Okay. And then you integrate here in omega with respect to x and y, and then you are taking the sum for all multi-indices. So if this quantity is bounded, then the function belongs to this fractional Sobolev space. Of course, in this particular case, So this is particular case of the general fractional sobular space. So arguing more or less like here, starting from the mean oscillation, writing this. So let me start at least with some initial steps. So in order to get this inclusion here, I start of course with the mean integral taken over some ball f of x minus the mean value of on the ball. And I'm considering this mean integral. Now I will do this way. I will write, so there you have f of x. I will write this mean value like the mean integral over b f of y dy. Okay, and here I have integration with respect to x. Now I consider here multiplication by 1, and 1 is exactly the mean integral of the constant 1. So this guy here could be written this way: integral over b, integration with respect to y, and here I have here x, and there is the mean integral. Okay, now concentrate on this term here, which is exactly f of x minus f of y. So I will put inside the modulus, so less than. This is integrated with respect to y. Okay, and then I have the mean integral. I have the mean integral.
And dx.
What?
And dx.
And then I have another mean integral with respect to x. Okay. Well, okay. At this point, I will apply the Hölder inequality. The Hölder inequality. Hölder inequality applied to this term here. And this gives the external integral remains as it is. So here I'm applying the Hölder inequality on this term with the exponent n over theta. So I will have the mean integral over b fx minus fy dy rise to n over theta, then integration with respect to x, and this is rise to theta over n. Okay? Now let us see this term here and consider this function f capital of t, which is the n over t over theta power of t. N is greater than or equal to, theta is less than 1, so this exponent is greater than 1. It means that this is a convex function. So I have this convex function applied to this mean integral. And I remember now the Jensen inequality. Jensen, which says that a convex function applied to mean integral of some f, some g, let us say g, is less than or equal to the mean integral of the convex function applied to the integrand. So it means, roughly speaking, that this exponent can be inserted inside this mean integral. And it becomes so I have the exterior integral, this exterior integral. So this will become the second mean integral, f of x minus f of y raised to n over theta dy I think it must be this way, or no?
Sure.
No, okay.
Both brackets.
Excuse me?
Two brackets. The first before the first integral.
Okay. One was missing. So, and the x theta over n. Okay. Well, now how to arrange this mean integration? I think Professor Nazarov knows it very well. So in order to arrange this mean integration, you have to divide to a suitable power of x minus y. So you will get, let me write it here. You will get a fraction. In the denominator you will have this guy here, f of x minus f of y raised to n over theta. And x minus y, now we have to so what will be 1 power n and another n, so 2n will be, must be 2n, in order to avoid this mean integration here. Integration over b dx dy. Okay, and now we can check very easy if you are right. So this 2n here, remember what is the starting space for f? It is this fractional Sobolev space there. So in our case here, so let me remember, f stays in w theta n over theta. So it means that this exponent here, 2n, I will have to check if it is n plus the decimal part of the first exponent, which is theta, and theta is between 0 and 1, so sigma is theta, times the integration exponent, which is n over theta. Okay, it is true. So, here is missing just theta over n. And now, so we got this inequality here, Here, of course, there is some constant, which depends on n and on theta. Well, now, making the radius of the ball small enough, letting it tend to 0, it is clear that this quantity once again tends to 0 because of the absolute continuity of the integral. So we have once again that the function will belong to VMO. Will be a function of vanishing mean oscillation. Well, let us go further. let me give you some examples. And the good examples are given, but by this family of functions. So let us consider a logarithm of modulus of x this way, rise to some power alpha where alpha is between 0 and 1. Even you can take also 1 included. By means of direct calculations or using some criterions I will give you later, you can check these inclusions here. That this function here, f these functions, so all these are VMO functions when alpha is strictly less than 1. Because of that, I took here a square root of the modulus of the logarithm. For each power alpha less than 1, you have VMO functions. Moreover, these functions stay in W1n, in the Sobolev space W1n, which is included in VMO, when alpha is less than 1 minus 1 over n. And even if they are VMO, they are not here when alpha is greater or equal to 1 minus 1 over n. So it means that it is true that W theta n over theta or even W1n is a subspace of VMO, but it is a proper subspace. So you have functions which are VMO, but they are not in the Sobolev space W1n. In case you take, for example, alpha equals 1, you have exactly the logarithm of modulus of x. It is a function which is in VMO, but it is not in VMO. So VMO and VMO, of course, are not identical. Another property. Suppose f is in VMO. And suppose that its VMO modulus is bounded above by some power, alpha power of the argumentar. So, how to see? Think about, for example, a function which is a continuous function which has modulus of continuity which behaves like alpha power of the argumentar. Then you can conclude that the function is Hölder continuous with exponent alpha. And here we have the same question. Let f be a VMO function. So generally it is discontinuous. But suppose you know that the VMO modulus of this function f is bounded by the alpha power of the radius r. What can we obtain? You can obtain the same, that f is C alpha.
I think it should be true also for Dini modulus of continuity.
Maybe. maybe I will arrive now at this result. Well, how to prove it? How to get this? So
again, this includes Lipschitz.
Maybe it is obvious. Excuse me?
Again, this includes Lipschitz. Like if alpha is 1.
Yeah, including also Lipschitz. How to get this? Of course, consider. So let us consider a ball with radius r. You are taking the mean oscillation. You know, taking supremo with respect to all balls r, this will be less than modulus of VMO modulus, and this is less than this quantity here. Okay, now this mean integral is comparable to 1 over r raised to n. Okay? Move this power on the left. So I will have that 1 over r raised to n minus alpha. There is the mean oscillation
n plus
less than some constant c.
n plus alpha.
Exactly, n plus alpha, n minus alpha. It's like my students do. Well, okay. And what it means for each r, it means that, so on the base of this hypothesis here, I'm concluding that f is in the Companato space with exponents 1, n plus alpha. And because the second exponent n plus alpha is greater than n, by one of the properties of the Companato spaces, I think it was the third property of the Companato spaces, you can conclude that f is in the Hilbert space with exponents. So it was lambda minus n over p. Lambda is n plus alpha minus n over p, which is 1. And it is exactly C alpha. It's exactly C alpha. Okay. Okay.
About singular integrals in VMO. Is it true that singular integrals maps VMO to VMO, like with BMO?
For BMO it is true, but for VMO no.
No.
We will arrive also to singular integrals somewhat later. Now, well, no, well, of course, a natural question to arrive is this. Given a function f in VMO, under which conditions on its VMO modulus we can ensure that the function is continuous? Because we have already seen that in general the VMO functions, they are discontinuous functions. So the question is, what conditions to impose on the modulus of continuity in order to ensure, what conditions to impose on the VMO modulus which guarantee that the function is continuous? So this is one condition. which gives you more, that the function is Hölder continuous. What about C0 here? What about the possibility to get only continuous functions? And so, given VMO, what conditions on the modulus of continuity ensure that the function is also C0? Maybe the more exhaustive answer to this question was given by Spanne, and he defined the space L phi in this way. So f is in L phi if the following quantity is bounded. As before, you are considering the mean oscillation, but there is another correction term, which is this function phi taken in the measure of b raised to 1 over n. So you can write also in terms of the radius. After that, you are taking supremum for each with respect to all balls, and the function f belongs to this space when this quantity is bounded. This quantity defines, of course, modulo the constant functions, defines a norm, and then it is the norm of this space. Note that if you take, for example, the function phi, so this quantity here is something, it is something like 1 over, so the measure of the ball is the radius raised to n. There is 1 over n, so you have here phi of the radius, okay, times the radius raised to n. So in case your function phi of t is t raised to lambda minus n, you obtain exactly the Companato semi-norm. So in this case, L phi is exactly L, the Companato LP lambda. L1 lambda. So, okay. We are almost out of time. So it is not difficult to get this result, that the space L phi is included in VMO if the function phi is infinitesimal in 0. If it tends to 0, like the argument approaches 0. In this case, if you have this condition, then this space is included into L phi, into VMO. It is almost immediate. What is interesting is that Spanne proved that if phi is Dian continuous, let me recall you that Dian means that this integral converges. Excuse me?
This is not Dian.
What is?
Dini is phi t divided by t.
No, it is dt over phi of t. This way.
You are from Italy, so you know better what is Dini.
So, if phi is Dini continuous, then L phi is included into C0. And this result is optimal.
No, I can understand. The less is phi. The less is phi. The worse is this integral, and it should be vice versa. Phi of t divided by t. This
Phi of t divided by t, of course. Phi of t divided by t, of course. Okay. Phi of t divided by t. And this is an optimal result. So you see that in this case, if where is it? No, when the modulus of continuity behaves like r raised to alpha, you get Hölder continuous function. But you can get a worst phi, and you will have only continuous function. Well, to finish with this space of function with Wagenschik mean oscillation, let me give you a characterization of VMO, which belongs to the same Saracen who introduced VMO. So the theorem of Saracen says the following are equivalent. F is in VMO. 2. F belongs to the VMO closure of Hooke of the space of bounded uniformly continuous functions. So if you have a VMO function, you can approximate it by in the norm of VMO by uniformly continuous function. 3. Consider the star norm, the VMO norm of this increment. And let the step reach to 0. Then you have this is 0. So it means in some sense that the usual molefiers, they approach the you can approximate a VMO function by the usual molefiers in terms of VMO norm. Okay, so what follows is the recall of some integral operators. I will use later, and the first one is known like Hardy-Littlewood maximal operator. You have a function f defined in Rn, which is L1 locally. with center at some point, at any point x, you are considering some wall, b, of x. Integrate the modulus of this function f over the ball with center of x. Take the mean value integral and then take the supremum. So radius r, the supremum with respect to all radiuses. This quantity, of course, depends on the center of the ball, and it is defined like the maximum function of f taken on this point x, and it can be defined for almost all point x. This is the so-called maximal, hardy little but maximal operator. It is true, of course, that you can control the modulus of f in terms of the maximal function of f for almost all x. What is interesting is the so-called maximal inequality. And I will give a number of this equation, mi, maximal inequality, which will be used later, which says that for each p greater than 1, you have that the LP norm of this maximal function is bounded in terms of the LP norm of the function f itself. Here the constant depends only on the space dimension and on p. So it means really that the maximal operator is continuous operator from LP into itself for each p greater than 1. Of course, by means of this inequality, you will have also for another constant c prime that also this inequality here. But what is interesting is this one, which gives boundedness of the maximal operator. Note that this is true for p greater than 1. And it fails when p equals 1 and also when p equals infinity. In particular, it will be not important for our further considerations, but just for the sake of completeness, if p equals 1, then what you can have is the so-called weak maximal inequality, which says that for each lambda greater than 1, considering the set of the points where the maximum function is greater than lambda, and taking the Lebesgue measure of this set, it is less than some constant over lambda times the L1 norm of x. L1 norm of x. For what concerns p equals infinity, so if you consider the maximal function defined on the essentially bounded functions, it is not true that M maps L infinity into itself. It is false. It is false. It is false. It is not true. But it is true that if you substitute L infinity with something larger, like BMO, it is true. So,
By default, no, it's strange. BMO to BMO.
to BMO, to BMO. So BMO is larger than infinity. It's larger than infinity. There are examples, roughly speaking, there are examples that starting from a function in L infinity, its maximum function is not bounded, but you can prove that it is BMO. So it means that this maximum operator is continuous.
If you substitute function from L infinity, yes, then this is just constant. M of f is bounded by constant.
It's bounded, yeah.
Yeah, so it maps L infinity to N.
Yeah, but you cannot prove continuity of the operator. So, roughly speaking, you cannot get this inequality with L infinity here.
But it's non-linear operator. What does it mean? This inequality also doesn't imply continuity in a sense. It's sublinear operator.
Yeah, it is sublinear, yeah.
Okay.
Okay, and the last argument is the sharp maximal operator. With the previous notations, Fy, the mean value, integration over y, both of radius r, you are taking supreme with respect to all radiuses, and this quantity of course depends on the center of the radius. So it is defined like the sharp maximal function. It is defined like sharp maximal function. The sharp maximal function. So it is the last note that by means of the definition it is related to BMO in the sense that f is in BMO when this quantity is bounded with me, which means that it is in BMO if and only if the sharp maximum function is essentially bounded. Well, and what will be used in the sequel is the sharp maximal inequality, which is known also as Pfefferman-Stein theorem. Which says that for each p greater than 1, you can estimate the LP norm of a function f in terms of the LP norm of its sharp maximal function. In particular, remembering also the maximal inequality, you have also that the maximal function is bounded in terms of the sharp function of f. This is, so this first part, this one, for the later purposes I will call fs, Pfefferman-Stein. Instead, this one here will be maximal inequality. So I think our time is over. I had prepared for also some recalls about potential theory, fundamental solution of the Laplacian operator, and some regularity results about the Newtonian potential, but maybe the next time I will start with these recalls. Because what is our next step is to extend these results about these regularity results about the Newtonian potential to more general integral operators. So I think to stop here. Thank you very much for your attention.